Hello everybody, welcome to Rainbow Use Case 1 webinar. Today we will talk about the contributions of use case 1, how we integrated Rainbow for our use case, how our application works, and a couple demonstrations to showcase how we deployed our applications and how they are working with robots, how they are controlling them. So today's agenda, it's not going to be a long one. So first, we will have an introduction to human-robot collaboration presentation from my colleague Aaron. And then I will present you the use case applications. So I will give a quick presentation about how they are working. And after that, I will show 2 videos demonstrating the first deployment of the use case applications and the use case applications in action. So we will be controlling one of the robots using the applications. So without further ado, Aaron, if you can take control of the screen and please, you can, oh wow, the recording is really putting a toll on my PC right now, but yeah.
Yeah, hello. Thank you for the invitation. And yeah, as you can see, the title is not human-robot collaboration, but human-robot co-work, and hopefully it will become a little bit more clear during my presentation in the next 15 minutes. I hope you can see my screen and understand me very well. And yeah, as Coral already said, I'm Aaron Heuermann. I'm researcher in BIBA as well, and I'm working in the field of human-robot interaction for already 6 years. And today I want to give you a short introduction into that field and start with a short motivation why human-robot co-work is such an increasing or growing field. And therefore, I brought you 2 charts, statistics from Germany, which fits to other European countries as well. And on the left side, you see the population of Germany divided into segments of 20 years, which means in the left bar, you can see the number of people below 20 years old, in the middle, the people between 40 and 59 years old. And as you can see, this middle bar is the highest one. And this means that many people are between 40 and 59 years old, and that are the persons who will leave their workplace during the next 20 or 25 years. And on the other side, you see the bar of the below 20 years old, which is much smaller than the middle one. And that are the persons who will enter their job life during the next 20 to 25 years. And this shows that more people will leave their job than new people enter. And this is and then the workplaces aren't filled and we need more workers. And the second chart is the one on the right side, and there you see the number of apprentices, and it's obvious that during the last 15 years the numbers of young talents who start their vocational education in very close to handwork jobs is decreasing, because more and more persons study and go to jobs at PCs, at office jobs, and not starting jobs in manufacturing. And these lack of young talents and the aging workforce are trends which makes it important to have a closer look on human robot interaction, because robots are a possible solution, or automation in general is a possible solution to handle these trends. And I will show you a small example of a manual workplace of power transformer assembly, and you can see that the worker is lifting these white coils from a pellet up to a work table. One of these coils weighs around 10 kilograms, and afterwards the human is starting to put sheets inside these coils from left and from right iteratively, and therefore the human has to count always 3 sheets for each side, and yeah, this job is very boring, but also challenging, because you have to count the right numbers of the sheets, and the tolerances between the coils and the sheets are not very big, and therefore it's very hard to automate this job right now. And as I told, one of these coils weighs around 10 kilograms, and the sheets which will be filled into the coils have a total weight up to 60 or 70 kilograms. So one finally assembled power transformer has a total weight of around 100 kilogram, and this heavy weight have to be handled by the worker manually, and the worker has to rotate the final product to make some adjustments, and hammering some further sheets inside the coils to make it completely full. And this is a task which is also not very easy to automate. And in this use case, you can see that on the one hand, we need to support workers, because if they don't have to handle that heavy weights during the job, they stay healthy, they can do their job longer, and don't start with retirement early. And on the other hand, there are jobs which can't be automated completely right now. And this is the motivation to combine the skills of humans with the skills of robots. And this is what we call human-robot co-work. Humans and robot work together in production processes, flexibly sharing tasks and contributing their respective skills. And as you can see in the strength and weakness table in the lower part, the weaknesses of the human: limited power, fatigue, the strengths of the robot: payload capacity, continuous operation, repeatability, and so on. So human and robot are a good combination. And let's have this current trend is also often in the newspapers. So we see title in the newspapers like "Colleague Robot," "Human and Machine as a Team," "Robot Becomes a Partner," and so on. But to make this vision realistic, some requirements have to be fulfilled. One requirement is the safety. So the robots needs to be safe and don't have to hurt the human. And on the other hand, the robot needs to have capabilities in the field of perception, cognition, and interaction to allow such close interactions between humans and robots. And we redesigned the process you see earlier to a collaborative one. So now the robot is putting the calls on the workbench, and the human don't have to lift it manually. And the robot is counting the sheets and provides them sequentially on the left and on the right side. So the human has to take the final counted sheets, and in the last step, the robot is overhanding some further components directly to the human hand. And by this redesign, the process is much more ergonomic for the human, as the human don't have to handle these weights very often. And also the annoying task like the counting of the sheets is removed. But let's have a closer look on this use case, and therefore we need to know about the different workspaces. So there's a workspace in which the robot operates, there's a workspace of the human, and of course there's a shared workspace in which both the human and the robot can do some tasks. And this is necessary to differentiate between different interaction levels of human-robot co-work. The first interaction level is the coexistence, and in the coexistence, human and robot don't share a common workspace. So you can see in the picture, while the robot is providing the sheets on the conveyor belt, you can see me standing behind the workbench, but I'm not in contact with the robot, and the benefit of this situation is that the robot can operate faster when the human isn't able to get in contact with the robot. And this one is called coexistence. The next interaction level is the cooperation, and that is that is the situation when the robot is providing, for example, the calls on the work table, because the robot is putting the coil on the work table, and after the robot releases the coil and moves away, I, as a worker, take the coil and do something else with it. So that's a sequential cooperation. Human and robot are in the same workspace, but not at the same time, so they don't have physical contact. And the highest level of human-robot co-work is the collaboration, and this is the current state of human and robot are in the same workspace at the same time and have a physical contact directly or indirectly, as shown in the figure. So I don't touch the robot, but I touch the piece which is gripped by the robot. And this is collaboration. And all these different types of interaction can be tracked using software. So we are able to receive the robot data, and we can track the human, for example, with a locating system. And then we can use this data to automatically identify the current interaction level and adapt the robot behavior according to this. And therefore, we need to follow this kind of decision tree. So we have to check if human and robot are in the same workspace. If no, it's coexistence. If yes, we have to check if they are at the same time in the same workspace. If no, it's a sequential cooperation. If yes, we have to check if there's a physical contact or not. And if there's physical contact and they are then at the same time on the same workspace, it's collaboration. And I told already at the beginning of this presentation that I want to talk about human-robot co-work instead of human-robot collaboration, and because I think that nowadays, too often human-robot collaboration is the topic, but most people talk about human-robot co-work, and we did this automatic analysis on a different use case, and as you can see in the colored figure in the upper part of this slide, there the different types of interaction follows after each other, and just the yellow parts are the parts where human and robot collaborate. So during an entire human-robot co-work, collaboration is just a small piece inside this. So collaboration are just episodes during work days, and that's why I think we have to talk more about human-robot co-work and less about human-robot collaboration. I talked a lot about interaction and recognition until now, so I told there's a different requirement which enables this, and this is the safety. And nowadays, there are many collaborative robots on the market which works with the principle of force limiting, which means that the robot is measuring an external force, and if there's a contact with an object or with a human, the robot stops automatically, and this is what creates the safety for the human, because this contact is not that hard that the human can be hurt. It's like a small push when you get in contact with another person in a tram, for example. Beside this very popular principle of power and force limiting to NL safety, there's another principle which is called speed and separation monitoring. And in this principle, you continuously observe the distance between human and robot and calculate the minimum distance and control the robot speed depending on this distance, which means when the human is approaching the robot, then the robot slows down until it stops completely when there's a distance of 0. And when the human moves away from the robot will speed up again. We did a lot of research in that field in BIBA, and probably Coral will tell you something about that as well. And we developed a variable sensor system in BIBA, which has these fibers attached to the work cloth, and at the red dots, the banding of the fiber is measured. So you know when the fiber is banded at this red dots, then the arm is banded there as well. And we use this to have a real-time digital twin of the human pose. And that data can be used to control the robot speed then, or to calculate the distance first and control the robot speed then. And when we attach such a sensor system to the human, we can't or we cannot use it only for increase or create safety. We can use the same data also for ergonomic analysis, for example. So I know if the robot, if the human bent over and have to lift some heavy part from a very unergonomic position and so on. So there are multiple benefits of such variable sensor systems, not only create safety in human robot collaboration. And that was my short introduction into that field, and I hope you learned something new. And I'm open for your question, or head over to Coral again.
Thank you very much, Aaron. It was really interesting and a really great introduction for what is the human-robot collaboration, or co-work, as you said, and what is collaboration inside this co-work. And it was really interesting to see how a robot can work together with a human. If there are no questions, I will continue the webinar with the second presentation, which is talking about the use case applications we are deploying using Rainbow. Use case. Can you see my screen?
Yes.
Okay, perfect. So again, everybody welcome. And this is the second part of our webinar. Now I will talk about the use case applications. So as Aaron showed us, the demonstrator we have here is to showcase an environment that human workers are working in collaboration with robots. In our demonstrator, it's a transformer. It is demonstrating a transformer assembly line. Here we have one worker working together with the robot, and another worker can join to this workspace. And let's say after packing off these transformers, another worker can come and take the basket and then leave the workspace again. So it's dynamic. In our demonstrator, we have two robots. One is Fanuc CR35IA. It's the green one, and the other one is Fanuc R2000IB. CR35 is designed for working together with humans, and R2000 is more heavyweight robot that can pick up and pack these transformers. And in our use case, we are controlling both of these robots. So the idea is to predict the collisions and, of course, avoid them. And for this, our requirements are, we need to make sure where the human worker is at all times. And this is called under the concept of asset localization. And of course, we also need to know where the robot is and what kind of motion the robot is doing. And to get this, we can use the forward kinematics approach for robots to get the position of the end effector. So we divide this to two, which is first is robot motion tracking, and the second one is personnel localization. First, for the robot motion tracking, we use the concept of forward kinematics, which is actually already researched extensively. And in this case, to use forward kinematics, we need to know where the robot is positioned at the base, which is not hard because at the beginning we installed the robot on the known coordinates. So by knowing the coordinate of the base of the robot, we can calculate where the joints of the robot, or basically the whole arm of the robot, finally the end effector, which is the actual hand of the robot arm, which is doing the heavy lifting part. So by if you can see my mouse, so by knowing where the base of the robot is and where the joints are, we can first calculate the where the all joints and the end effector, and then by knowing the other attributes of the robot, we can create a whole contour of the robot and know where the robot is in the workspace in real time. So by using this, we can track the robot in real time. And the second service or second part is the asset tracking, is the personnel localization and motion capturing. For this, we are using an indoor localization system, and an indoor localization can be done in multiple ways. It can be simultaneous localization and motion capturing, monitoring-based systems. We can use inertial measurement units, wireless-based systems, and visible light or ultrasound-based systems. In our demonstrator, we are using a wireless-based system using tags, and these tags are emitting ultra-wideband signals. So there are lots of other technologies that can be used with different pros and cons. In this case, because of its better accuracy, we opted to use ultra-wideband. So how can we localize something using ultra-wideband tags? There are multiple methods such as time of arrival of the signal, time difference of arrival, angle of arrival. This means that our tags are emitting signals and responding to signals that is coming from anchors. So we need to put lots of anchors to our workspace, create the boundaries. These anchors are talking with the tags. Here, as you can see in, let's say, in the trilateration. So we can have three anchors that are talking with one tag, let's say in between. So these tags and anchors can communicate using the time of arrival or received signal strength, and we can extrapolate the location of this tag. So basically the asset we want to track, and in this case a human worker, by using multiple techniques. One can be trilateration, one can be angulation. And as I said, ultra-wideband technology can provide accuracy as high as 10 centimeters, which is a great accuracy. But again, because it's a wireless technology, it is prone to noise, which is a problem with any wireless technologies. So in an ideal condition, ultra-wideband technology provides really good accuracy. But if you are working in a workspace that has at least metals, and in this case, it's a transformer assembly, so there are definite metals, the noise can provide a challenge. To mitigate this noise somewhat, we also use a robust adaptive Kalman filter. This mitigates some of the noise because it makes the application more resilient to sudden changes. Here in the picture, you can see two tags, two ultra-wideband tanks with a power bank that is powering them. That is used for human localization. So as I said, we have two methods, so two things we have to figure out. First, tracking the robot and tracking the human. We create two services that are doing this, and we have a third service that combines this information and then predicts and avoids the collision between humans and workers. So you can see a table of how the applications are work. So in this case, we have human workers with ultra-wideband tags connected to them, and they are emitting signals telling where they are. And we have a data aggregator that collects all these signals and then gives this information to a personal localization and motion capturing service. So it can be calculated where the human workers are, the exact positions. And we also have two robots which are communicating with the industrial PC. And then we get this information from the industrial PC and provide this information to robot motion tracking service. So we can get the exact location of the robots in real time. And we have finally a collision prediction and avoidance service, which again combines these informations. To deploy these applications using Rainbow, we opted to use a microservices architecture. In a microservice architecture, a big service is divided to microservices. And in our case, so instead of the whole one collision prediction service, it is three smaller services. One is robot motion tracking, one is personal localization, and finally the collision prediction. This enables us better maintainability of our software, better testing, but first, most importantly, we can scale these services much easily in the microservice architecture, and Rainbow provides us the tools to be able to scale them much more easily. Because we are using a microservice architecture, we need a way to communicate these services together. So we can aggregate the information from one service to another. And for this, we are using advanced message queuing protocol and using RabbitMQ for event queues. So one service gets an information using event queue, processes it, and puts in another queue that another microservice will read. To enable scaling our applications, that means we will have one application microservice, so one service running multiple instead of one. The services needs to be stateless, so they should not require knowledge of the state, or they need to acquire this state from some other service, because two microservices with the same objective must be in the same state to be able to scale. And for this, we use Redis. Basically, after each processing, we push our states where the people are or where the robot is to Redis. And then another service can take this from Redis. And we are using Redis because it's an in-memory database, so it's really fast. So you can see a figure here that is, again, showcasing how we are deploying them. Again, we have a data aggregator and industrial gateway to collect the data. These data is published to event queues using RabbitMQ. And we have our microservices, which are RMT, robot motion tracking, PLMC, personal location, and CPA, which are using, again, RabbitMQ for communication between each other. And finally, the collision prediction and avoidance service, if there is a collision that is predicted, sends a stop signal to the robots, or it can also send speed messages to the robots, depending on how the human worker is close to the robots. So you can right now find all these microservices in a Dockerized way in the Docker Hub using this link, hub.docker.com virtual origami under virtual origami user, and play with them if you want to. We have the avoidance service, all three avoidance services, so collision avoidance, personal localization, and robot motion tracking uploaded, and we have two data generators also uploaded to the Docker Hub. This